Hi, welcome once again in this comprehensive course of indefinite integrals, and slowly we have reached to lesson number 13, which is a special line. The special line are 9 important results. We can apply them to find the integral of some special integrands. So this the derivation of special line is based on the technique of inverse substitution, which we have learned in the previous lesson. So let us try to derive some of them, and then we apply them into the direct problem. So they are special 9 results, the integrals. So the first one is 1 over x square plus a square, and the integration will be 1 over a tan inverse x by a plus c. And similarly, you can see these are 9 numbers. We can see the first format, the first set of 3 will be 1 over x square plus a square, x square minus a square, or a square minus x square. Similarly, the second set will contain the same thing, the combination of x square and a square, but in denominator we will have the square root over it. And similarly, the third set will have in the numerator and no rational. Actually, this is an irrational, a square minus x square, the square root of a square plus x square, and square root of x square minus a square. So you can see that the only the combination of x square and a square is happening in different form. The derivation of first 2 sets, the first 6 integrands, like from here to here, are actually done with the help of inverse substitution, and they can be done easily. But the last 3, that means these 3 integrations can be done with the help of inverse substitution too, but the integration by parts will involve into it. So I will simply suggest to try these first 6 derivation only, and once you get the idea of integration by parts, you can also derive it. So just try to derive this this 1 over a square minus x square dx. So this is what 1 over a square minus x square, and the derivation should be, the result should be 1 over 2a ln a plus x divided by a minus x plus c. So we will derive it. So what we can do, we can simply see that the inverse substitution process should be done, and we can say that a square minus x square is the standard form in which we have to substitute x equals to a sine theta. So we'll do so. So x equals to a sine theta, as soon as we get, dx will be a cos theta d theta, and of course after substituting this back into the integrand, we will have a square minus a square sine square theta in the denominator, and a cos theta here at the place of dx. So now this a square can be taken out, and this 1 minus sine square theta can be written as cosine square theta. Let me just evaluate this quickly. So this will be what? A square, and this will be sine cos square theta, and of course there is a cos theta d theta in the numerator. And now you can see that a and a will get cancelled, so this 1 over a can be taken out, and this 1 cosine theta will be cancelled with 1 cosine theta. So we will have integration of sec theta, and you know the integration of sec theta is sec theta plus tan theta, log sec theta plus tan theta. So this is so, but we have to write the answer in form of x. So in the form of x, so we have to just convert this theta into x, so with the help of any function. Suppose x equals to a sine theta here, so sine theta can be written as x over a, and we will have a triangle in which the perpendicular is x and the hypotenuse is a. So of course the base will be square root of a square minus x square. So from there we can take sec theta as a over square root of a square minus x square, because it is hypotenuse by base, and tan theta as perpendicular by base. So in this result, we will substitute sec theta and tan theta in terms of x. So this will be a over root over a square minus x square, and this is x over root over x square minus x square. The base is same, so we can simply add the numerator, and of course this a square minus x square can be factored in the form of a plus x, a minus x, and you can see this is a plus x to the power 1, and in denominator we will have a plus x to the power half, so we will have a plus x to the power half in the numerator too. So from there we can write this in this form, ln square root of a plus x divided by square root of a minus x, and so we can write it in this form also by taking the entire power as 1 by 2, and after using the property of log you can take this half in front and you can get the final result we had to find. So this is the way to derive, and I suggest you to derive all the other 5 results, and if you simply observe that this result particular we have done in the previous lesson, so only 4 results you have to derive, and I actually suggest you to simply go for it. And these 3 you will be recommended after doing the integration by parts, but if you are done with the integration by parts you can easily derive it also. So now let us try to apply this result in the problem. So there are two kind of problems. The first is we can directly apply the spatial line, any of the spatial lines. So there are 9 important integrals or the results, and we can apply them directly. How? Suppose I have to integrate the square root of x square plus 8, so we can just simply write in the form of a square root of x square plus a square, and we can observe that the integration of a square root of x square will be x by 2 square root of a square plus x square plus a square by 2 ln x plus the square root of x square plus c. So here you can observe that this is a and this is x, so we have to substitute the value of a here only, and after simplification we can get that answer. This is a very easy thing. Again, suppose I have to integrate 1 over square root of x square minus x square, so we can write x square minus 16. So here we have to write 16 as 4 square, and again this is the particular result we have to use, where in which we have to substitute a as 4, and this is the correct answer. But sometimes we have to substitute before we use the spatial line, and with the meaning of that, let's try to understand it with example. So suppose I have this integrand as cos x divided by 9 plus 4 sine square x. So of course we can see that 4 sine x sine square x can be written as 2 sine x the whole square. And if I do so, we can easily understand that 2 sine x is the candidate of substitution, because the derivative of sine x is cosine x, which is present in the numerator which is attached with dx. So this is the main idea of the substitution. So of course let us substitute t is equal to 2 sine x, so we will get dt by 2 as cosine x dx. So this cosine x dx should be replaced with dt by 2, so half can be taken out because it's constant, and in denominator we will have 9 plus t square. And of course this can be written as 9 as t square, and it's a t square, so we will have 1 over a square plus x square format, and from there we can apply the special result or special line, and that is what 1 over a tan inverse x by a, and so this is the 1 over 3 tan inverse t by 3, and after simplification we will have 1 over 6 tan inverse, and since t was 2 sine x we can substitute it back. So you can see that before applying the spatial line result we have to substitute first. So this is the idea we have learned from it. Now let us try to apply the similar thing, the substitution before using the spatial line in this particular example. So this is the example where the numerator is 3 to the power x, and in denominator we will have 25 plus 9 to the power of x. So of course this 25 can be written as 5 square, because we need 1 over we can see that we can actually foresee that this will be in the form of a square plus x square. So of course this 9 to the power x can be written as 3 to the power x the whole square. So this 3 to the power x can be substituted. So t is equal to 3 to the power x, and dt by dx will be 3 to the power x ln 3, and ln 3 is constant, so they can be adjusted here. So for 3 to the power x dx we will substitute dt over ln 3, and ln 3 is constant, so we can take it out as 1 over ln 3 here, and in denominator we will have 5 square plus t square. So again we have the similar integration 1 over 5 tan inverse t by 5, and since t was 3 to the power x, we will have this as the final answer. This is another example in which we are doing the same thing, that is substitution before using the special line. So here this is x to the power 3 square root of 100 minus x to the power 8. So you know that the x to the power 3 is somewhere like the differentiation of x to the power 4, I mean the factor of derivative of x to the power 4. So x to the power 8 can be written as x to the power 4 the whole square, and why not we can substitute this x to the power 4 as t. So this t is x to the power 4 here, so derivative will be 4x cubed and dt by 4 will be x cubed dx. That means this x cube and dx together can be replaced with dt by 4, and since 1 by 4 is constant, it can be taken out, and we have this thing, a square root 10 square minus t square. So we will have this is in the form of root over a square minus x square dx, and you have the formula in the previous slide. You can just go back, or if you have taken the note, you can simply match this as the answer in form of t, and since t was x to the power 4, you can replace it back, and that is the final answer in the form of x. So this is the example here, 1 plus ln x 2x square ln x whole square. So again you can see that if you have done a lot of practice on substitution, we can see that 1 plus log x is the derivative of x ln x. So we can write this x square ln x as x ln x the whole square, and you can take this x ln x as t, so the derivative will be 1 plus ln x dx, and of course the substitution will be happen, and that will be in the form of dt, and this will be root 2 square minus t square. And again you can see the form of special line and write the correct integral in the form of t, substitute it back the value of t there, and that will be the final answer. So I will not going to do this question, and you are requested to do this, and I am sure that you can do this very easily. So that is all about the special line. So the one important thing I want to mention here, that all the special line formulas should be committed to your memory, so that you can apply them directly in dealing with some problems. And again, you don't have to derive any of them formula while you are doing the problem. You have to apply it directly, but I recommend you to derive it before jumping into the question, so that you will be able to learn how it has happened, and it will be easy to learn or memorize in the process of derivation. So that's all about today. That's all about today's video. Thanks for watching.